Okay, let's do some control volume examples. So let's imagine I have a block, which is a solid, and it has an angle theta. I'm going to take my garden hose, which has a cross-sectional area A, and I'm going to spray it at the block. And what I want to know is what's the force exerted on the block. So let's draw a control volume. I'm going to draw it to enclose the block. And everywhere I cut through the stream, I'm going to make the normal vector of the control volume align with the flow. Perfect. Now let's make a few assumptions. First of all, I'm going to assume steady flow, so we're not interested in any transients. So I'm going to assume steady flow, so we're going to ignore all the transients. I'm going to neglect gravity, and we're going to assume that the area of the jet is the same, so the area coming in and out will be the same. So let's write out conservation of mass first. Okay, there's our statement of conservation of mass in integral form. And since it's steady, I can get rid of that term. And since it's steady, I can also, since this side is 0, I can basically get rid of the minus sign. And so I just have rho v dot n on my boundaries. So I really have two places to worry about it. I'll label them 1 and 2. So I have flow coming in here and going out there. Now if we're going to assume that the velocity coming out is uniform, then the velocity at 1 dotted with the normal vector will be negative, since velocity is in this way and the normal vector is outward. We're going to have the density of the fluid rho, and we're going to have the area of the jet A. So that's at surface 1. At surface 2, the velocity is aligned with the normal vector, so I have plus u at location 2. I have the density of the fluid, and we're assuming the area of the jet is the same, so A1 equals A2 is equal to A times A. And that equals to 0 because it's steady. So now we see the density and the area cancel, and this tells us what we probably could have guessed was that U1 equals U2 is equal to just the velocity of the water coming out of the hose. Okay, now let's consider momentum in the x direction. So we have several terms here. We have the time rate of the change of the momentum in the control volume, the flux of momentum in and out, the pressure, gravity, viscous stresses, and our external force. Since I drew my control volume to sort of enclose the block, we need to imagine that there must be some external force which has an x and a y component that's holding the block in place. And so my external force I'm going to draw with the assumption that it's positive, so I can just conclude it as a positive number here, and the sign will work out in the end. Okay, so let's look at our assumptions again. So by steady flow, I can get rid of that term. By neglecting gravity, I can get rid of that term. And then also, if we just think a little bit physically here, the pressure, this is just the jet in air, it's just the atmospheric pressure. It's the atmospheric pressure here. It's kind of the atmospheric pressure everywhere. So there's no reason for us to build up pressure inside the jet. So there's no net pressure forces acting on it. It's just atmosphere pushing on it everywhere. So in the end, we have flux of momentum, external force, and the viscous stresses. However, these are the viscous stresses evaluated on the boundary ds. So we know that all the viscous stresses, if there were any to worry about, would be located along this surface. And so what I'm going to do is sort of say, let's cut our boundary here and here. And so in that case, there would be actually no viscous stresses at this location and this location. So along the surface then, the viscous stresses are 0 because we're just looking here and here. And so in this case, any viscous stresses would be wrapped up into the external force. Now this is a little bit subtle, so we'll actually deal with this in the next problem. But let's just move forward saying there's no viscous stresses on the surface of our control volume. Okay, So now let's evaluate all the terms. We have to be a little bit careful with the sign. There's a negative sign here. This rho v is a vector, so we have to worry about the sign there. And v dot n can have a sign. So we have kind of three negative signs we always have to keep in mind. So our equation then is that 0 is equal so on surface 1, rho u is the momentum coming in. V dot n is just u with a negative sign because the normal vector points out, the velocity's in, so that's negative. And then I have ds, we're just assuming it's constant over the area of the jet, so it's just multiplied by a. At surface 2, rho v, right, v is a vector, so it's rho u cosine theta. V dot n, in this case, they're aligned, so it's just u times the area of the jet. And that's equal to 2. Plus the external force in the x direction. So what does that imply then? That implies then that the external force f of x is rho u squared a cosine theta minus 1. And that makes sense because cosine theta will be less than 1. So this will always be a negative number, so our force will have to hold the block in this direction. If the angle were 0, then this would be 0, so there'd be no force. If the angle were 90 degrees, the force would be maximized and negative. Now let's consider the y momentum. And then again, we can just look at this expression up here. So we have 0, because it's steady, is equal to, again, we have our negative sign. On surface 1, there's no vertical velocity, so rho v is 0. On surface 2, rho v is rho u sine of theta, because that's the vertical velocity there. And the flux out of it, v dot n, is aligned in positive, so it's just u times the area plus the external force in y. So that implies then that the force in y is rho u squared a sine of theta. And it's positive, so it's a force upwards. So when the angle is 0, there's no force holding the block upwards. And as we change the angle here, it gets steeper and steeper. Then the force pushing the block down gets stronger and stronger. And that's assuming that all the flow goes in and out and up, which could be a faulty assumption for high angles. Okay, now let's do a similar example as the last. But let's pay a little more closer attention to the viscous forces at this time. So let me just take my surface to be horizontal. And again, I'm going to spray a hose at this. Okay, so we're going to have kind of the same problem as last time, except I'm going to kind of relax one of my assumptions. So I'm still going to assume it's steady, so we're not interested in transients. But now I'm going to relax the assumption that A1 is equal to A2. And by A1 and A2, I just mean we'll draw a control volume, again, to include the plate. We'll call this surface 1, this surface 2, with normal vectors pointing outwards. So we're going to simply relax the assumption that A1 is equal to A2. Conservation of mass, just like in the last problem. It's steady, so that term is going to go away. So we just have the flux of matter coming in and out. So here we have the velocity at 1 times the area 1 times the density equals the velocity at 2 times the area at 2. Now the density will cancel, but since we're going to relax the assumption that A1 is equal to A2, then we simply have that U2 over U1 is A1 over A2. Now let's go to conservation of momentum. Here we only have x momentum to worry about. I'm not going to write the gravity term because we're just going to cross it out in the end. I have my viscous stresses that I'm just writing as the viscous plus my external force in the x direction, because again, I need to apply some force to this plate to hold it in place, presumably. So, as before, we have P atmosphere. It's a jet that's free in air, and so by the same argument as before, we're really not going to have any pressure to worry about. The pressure is just, in the whole system, is basically going to be at P atmosphere. So the pressure term isn't going to do much. It's steady, so that can be 0. And again, by the same argument as before, the viscous stresses here, at this exit here where the jet is free and at the entrance where the jet is free, are basically going to be approximately 0. So I'm going to neglect those. So we have the same expression as before, where the external force is the change in the flux of the momentum. So let's work out what that is. And again, let's be careful about our sign. So we have a negative that comes from here, a sign that shows up in the velocity vector, and a sign that shows up in v dot n. So again, I've been careful with my sign. I get a negative sign here, and I get a negative sign in this term because v dot n is negative, because the velocity and the normal vector are not aligned at state 1. Here it's positive, and that's my force in the x direction. Now we might notice from conservation of mass, u1a1 equals u2a2. So this u2a2, I can cross out and substitute with u1a1. And I could rearrange this expression to be the force in x is minus that. So we expect the force to be negative because I expect that I'd have to hold the plate in place, otherwise it tends to want to move in that direction. And so that tells us that u2 should be less than u1, which if we look at this expression here, tells us that a2 should be greater than a1. So the jet should come in narrow and fast, and it should thicken a little bit if it does anything. Now we can relate how much it's thickening, or what's going on here, to the viscous stresses. Because if you imagine, instead of the control volume I drew, I cut right along this surface here, then just Newton's laws, which tells us the force has to be equal and opposite at the surface. If I slice it here, tells me that the viscous stresses have to equal this force that we're holding things in with. And so what that means is that this term here, if there are any viscous stresses acting, on this surface along here, if we have viscous stresses along here, our momentum balance would tell us that we expect this jet to thicken and become slower, so it has more momentum coming in than out, which is sort of offsetting the forces which are going in that direction. And so if there are viscous stresses that we want to worry about, our conservation momentum doesn't give us any way to actually calculate what those are unless we make some other assumptions. But it does tell us the direction things go, and the fact that if in fact there are viscous stresses, this thing needs to thicken, and A1 is not equal to A2. So in the previous problem, where we assumed that A1 equaled to A2, that would be consistent with assuming that the viscous stresses are negligible along the surface. Okay, let's just move on with a few more examples just to sort of see how things work. Okay, so let's assume we have a 90-degree bend. We have a flange here which is bolted together to a pipe, so we have fluid flowing in our pipe here. The exit velocity here is u. The pipe is size, cross-sectional area A, everywhere along here, so we won't worry about the area change. But there's sort of this 90-degree bend right at the exit. And what we want to know is what are the forces that are acting on these bolts here. So what force do we need to hold this thing in place? So we'll draw a control volume to cut like that. We have normal vectors pointing out in that direction. And now we need to talk about what our assumptions are. Ignore transients, it's steady. Let's neglect gravity. We're going to neglect viscosity, so we'll assume there's no viscous stresses. So we're just interested in how much momentum there is, but by turning, it wants to sort of pop this little 90-degree bend off. And finally, let's assume if we label these surfaces 1 and 2, let's assume that the pressure at 1 is approximately the pressure at 2 is approximately the pressure of the atmosphere. So there's basically no real pressure loss around this last little bit of the bend, so the pressure doesn't change much between here and here. Now in reality, this pressure would be a little bit higher, which would exert a force maybe that would be a little extra than we'll calculate for wanting to pop this thing off, but we'll just assume that there's basically no losses in this bend. So let's write out our conservation of momentum in the x direction. So there's all our terms. By the steady assumption, that one goes away. By the neglecting gravity, that one goes away. By neglecting viscosity, that one goes away. And by saying the pressure is basically everywhere p atmosphere, that term goes away. So all we're left with then is the flux of momentum and the external force. So when we do the x component of the momentum, let's again be careful with our signs. So for the x momentum, there's velocity here, right? So rho v is just rho u on this one, which is that term there. And v dot n is u, but with a negative sign, so that's that term. But at this surface, at 2, there's no x component of the momentum, so it's just 0. So we only have x momentum here, which is being turned, and that has to be balanced by f of x, which is pushing back on this thing because it turns out to be negative. So it's our force holding that in. Our y momentum will be very similar, so we'll have 0, because rho v is just rho u, because the velocity here is the same as the velocity here because there's no area change. Here v dot n is positive, so that's just u. So the force in x and the force in the y are the same. Force in y is holding it up because the momentum flowing out that way makes the nozzle want to shoot downwards. Whereas the flow this way, which is turning, we have to push to hold the nozzle in. Now let's do one where we apply Bernoulli's equation and a control volume. So again, we're going to have a pipe with a flange where we want to know essentially the force on those bolts that's holding this pipe together. We have velocity u here. Except now, we're going to have a nozzle that comes down, reduces in diameter. So it squirts out a lot faster than it comes in. Upstream, we're going to have area A1. Downstream, we're going to have area A2. Upstream, we're going to have velocity U1. Downstream, we're going to have velocity U2. Now in this problem, we'll draw a control volume to go right down the cut directly like that. Seems like the obvious choice. And now we're going to talk about what our assumptions are. Again, steady. So we're going to assume the flow is steady. We're going to neglect gravity. We're going to neglect viscosity. Now we could write it out, but I think we know by now that conservation of mass is going to give us the following relationship. It's going to tell us that U1 times A1 equals U2 times A2. Now we should note when we write this, what we're really assuming is the velocity profile here is roughly uniform, or we can capture it as such. So a mean velocity times the area is kind of good enough for our analysis. So we're not really worried about the velocity profile here, whether it's a parabola or some other shape. But since we're neglecting viscosity and its high speed, it's usually a pretty good assumption to assume that things are rather blunt and, at least in a net sense, uniform. So that is an assumption that we're really not solving for the detailed velocity profile. We're just saying it's basically uniform. So it's just the velocity times the area to get the total flux of mass crossing the surface. Okay, now let's do momentum and we'll write all our terms out. And here we're really only going to have momentum in the x direction because there's nothing happening in the vertical direction. So again, we have the change of momentum in the control volume equals the net flux in and out, the net force due to pressure, gravity, viscosity, and our external force. By our assumptions of neglecting gravity and viscosity, I'm not even going to write those out. They're just 0. And by our assumption of steady, I could also just say that that's equal to 0. So now we have net flux of momentum in and out of our box, pressure, and our external force. So again, being careful with signs to make sure we get everything correct. We have this negative sign to worry about, the sign here of rho v, and our sign here with v dot n. So as before, we have the sign of rho u, which is going to be u1 and u2 at entrance and exit. We're going to have u dot n being negative here because our normal vector points out. We're going to have u dot n being positive on this side because the normal vector points out. So we've seen all this before. Now let's do the pressure. The pressure we have to be a little bit more careful about. So we have a negative sign here. And at surface 1, the normal vector points outward in a negative direction. So we have minus p at 1. We have plus the pressure at 2. Now I need to be careful with the area. So this is going to be A1. This is going to be A2. But we have to be careful with the rest of the control volume as well, because we have to consider the pressure acting on every surface. So here we have the pressure of the fluid at the exit times A2, but we have over this, maybe I should draw that in red actually, over this projected area, we also have the pressure of the atmosphere. And it's pushing back in the negative direction, so I'm going to add it as plus P atmosphere times A1 minus A2, acting over that stuff. Now, we could also worry about the pressure acting here, but once we're outside the pipe, atmospheric pressure pushes this way and pushes that way, so it balances. So I'm just going to worry about the area just around the pipe. And that has to equal our external force. Now, however, since this jet is exiting to the air, and it's just exiting in straight lines, the pressure of the atmosphere is the pressure at the jet. So we can substitute the pressure at 2 with P atmosphere. And now we see that P atmosphere times A2, P atmosphere minus A2, this term will cancel with that term. And so the net force due to pressure is just the pressure at 1 relative to the atmosphere times the area of 1. So let's write all our terms out and see what we think about the sign. So our f of x, let me make one last change. So we have u2a2, u2a2, that's the same thing as u1a1, so I can cross those out. Right, this is u1a1. So when I rearrange the terms to one side, we have the force is equal to some change in momentum term, which we'll have to work on just a little bit more, times pressure at 1 minus the pressure of the atmosphere. So let's think about the sign of this term here. If this pressure is higher than atmospheric, this is positive, so it wants to pop the nozzle off, so we have to exert a force in that direction. So I like the sign of these terms. u2 over u1 here, we can also replace with A2 over A1, right? Because our conservation of mass would tell us that U2 over U1 equals A1 over A2. So there's our expression for now for the force. If we look at it, A1's greater than A2, so this term is positive. We expect P1 to be greater than P atmosphere, perhaps. Which would tend to pop that off. So it's not clear what the sign of this thing is because we sort of have pressure and velocity. So we can make a little bit of progress here if we actually apply Bernoulli's equation. So let's apply Bernoulli's equation along the streamline running from 1 to 2 right down the middle. So we'll do that over here. So that's going to tell us that the pressure at 1 plus 1/2 rho U1 squared equals the pressure at 2, which is P atmosphere, plus 1/2 rho U2 squared. So I can rearrange this to be P1 minus P atmosphere equals 1/2 rho U1 squared minus U2 squared, which is going to be a positive number because U2 is going to be greater than U1. So this is going to be a positive number, so we expect the pressure at 1 to be greater than the pressure here at the exit, which makes sense from Bernoulli's equation because the velocity is high here, so the pressure is low. So we can substitute this expression into here for P1 minus P atmosphere. But before we do that, let's get this in terms of U1 and area 1. So P1 minus P atmosphere. So now we have a factor of A1 over A2 squared. So let's make this substitution. So we get a final estimate of the force to hold this nozzle on in terms of the inlet velocity and purely just the ratio of the area. So A1 over A2 minus 1 minus 1/2 A1 over A2 squared minus 1. Turns out that if we evaluate this for A1 over A2 being greater than 1, it's always negative, which goes with our intuition that if we have a hose and we attach a nozzle onto it, it's going to pop off unless we screw it on. Okay, let's do one final example where we have gravity in the problem, just to do one of that. So let's do our hose. Let's just squirt our jet out into the air. I'm watering the garden. So here's my jet. It's coming out with velocity U, area A. I'll draw a control volume as such. Gravity will point down. So we're just going to assume that the area of the jet doesn't change, so the area here is the same as the area here. Therefore, the velocity here and the velocity there will end up being the same. So we're not going to worry about conservation of mass. So let's look at conservation of momentum. Let's look in the x direction. So we'll do steady again. So we'll say that's equal to 0. So we have the flux of momentum coming in and out, we have gravity, we have the pressure, we have the viscous stresses. Now, as before with all our free jet problems, since this is P atmosphere, this is P atmosphere everywhere, we don't expect there to be any effective pressure. And since this is a free jet, we really don't expect viscosity to matter here, so we're going to cross viscosity out. So our conservation of momentum, we have two components, which is the flux of momentum in and out, and gravity. When we look at things in the x direction, there is going to be no gravity. And so we've done this enough before that I'll just sort of write the terms out. So this is surface 1, this is surface 2. We have a negative sign. We have rho u coming in. We pick up a negative sign. We have u on the other side. We have a. And then on the exit, we have rho u, u, a. So those cancel. So conservation of momentum, stuff comes in, stuff goes out. Now let's look at the y direction. So this expression still holds, so we have 0 equals. Here our flow is coming in, and it's perpendicular, so there's no component. Here, though, something has to happen because we're going to include gravity. So let's just assume there's a little bit of flow downwards, v. I guess I should assume that it's upward and let the sign sort of work itself out. So we have a negative, this negative here. We have rho v, so I'll use script v, so the vertical velocity. And then v dot in is the flux of that leaving that, so that's u times a, times the area of the jet. And that has to balance rho g, which is negative because gravity's pointing downward, so I'm going to flip that sign to be negative. And I need to integrate that over dv. Now the volume of the thing we can just approximate as the area of the jet times the length. So this would be 0 equals minus rho v u a. So the area times the length, that's the length L. So we get the vertical velocity is negative, so it's flowing downwards, is GL over U. So that means that our jet is sagging, which makes sense. And this also makes sense if we think about just sort of from a particle perspective. If I have G pointing down, and I take something and I drop it, its velocity at any given time is minus G, because it's going downwards, times the time, how long it's been falling for, right? So in our case, the time that it's been falling for is this length divided by that velocity. So if I just substitute that in for the time, it's length divided by velocity. So we get the same result. So this is just to show you sort of a simple, sort of trivial example that if we include gravity, yes, things in fact do work out as we would expect.